So purely and simply, this is the same first page as we had the other day. Barring any other questions, I guess I'll start rolling. I suppose the general theme was that to be able to get energy out of these systems, we need to be able to have a heat transfer fluid. And the rate at which heat gets transferred to that heat transfer fluid is usually by conduction in some of these reservoirs, and would be also in ground sourced heat pumps places. Yeah, someone can grab that. And so we need to understand something about how it circulates and what rates it circulates. That's next week. But for now, we need to know something about equations of state and thermodynamics of those systems. So typically, heat is carried by conduction to the fluid, and then the fluid is used to drag it out of the subsurface, and then something is done with it. And usually, to recover the heat from it, it's most efficient, or the highest energy yield is if it's a phase change, because we can use that phase change to drive conventional turbines. So we want it to be 100 degrees centigrade plus if as desired, but we can also do it by transferring heat from the water to a second fluid in a closed system, a binary system, that boils at, say, 40 degrees centigrade, in which case we can do the same thing. It will boil at 40 degrees centigrade, run it through a turbine, capture it, condense it, and then keep it within the system. So to do that, we need to understand something about thermodynamics. So we'll carry on with the first law from last time and talk about the second law as well. So we talked about this in 303. It was a brief section. Certainly if you might have taken 301 at the same time, thermo, but certainly we talked about it in 303, and it fits into the kind of framework of fluid mechanics and physical behavior. So certainly the difference between thermo on one hand and fluid mechanics is that you're dealing with a physical system with kinetic energy in one case, and you're dealing with a system with chemical-like energy, heat energy in the other case, but they are related. And so if you look at the first law, as defined here, I guess, won't it go any larger than that? I don't know why it won't. It will. Just have to do it there. Just want to do it on my pad. And that is, if you write the first law as we talked about it last time, I don't know why it reset, but it did. Then we had, it needs this for some reason. Then we drew this merely as a little box that was, shouldn't be quite so blunt, I guess, but it's because it's magnified that's that case. We had this block that we had Q in, work out, and delta U. And the statement really is just that if it's a balance between the amount of heat energy coming in, the amount of work the system you're using to do. If they don't balance each other, then you net accumulate internal energy. Internal energy per unit mass, as we discussed in fluid mechanics, but it's a very simple conservation of energy system. It's a control volume with fluid in it. So you can think of it as a zero-dimensional system, right? This is just a box or a bucket that stuff is coming into and stuff is going out of. It has no real dimension or geometry to it. And if you do that, the statement is really, that's exactly the same statement as above. Thermal energy in versus out, work in versus out is equal to the accumulation of energy in the system. You can use Reynolds transport theory on it. You can define the total energy per unit mass within the system as the sum of the internal energy per unit mass and two of the three components of Bernoulli. Velocity head, which is kind of kinetic energy, elevation head, which is potential energy, and pressure. And of course, pressure is kind of wrapped up into this because internal energy is equal to, it's a blunt instrument, enthalpy plus pressure. It's written somewhere. No, it's the other way around, isn't it? So enthalpy is equal to internal energy plus pressure, I think, over density. Right? Yeah, over density, because it's per unit mass. And so the other term, the pressure term, which is missing, is just rolled into this component here. And so if you look at that along a streamline, which is exactly what this was, then you get an expression which includes all of those components. You have at the upstream end and a downstream end. I should have a less blunt instrument than that. You have a pressure downstream, you have a velocity downstream, and you have an elevation downstream, and likewise upstream. And in addition to that, you could imagine that you can potentially put thermal energy into the system. That's all we're saying. So in addition to the system, you can have components moving through here, and of course you do have components moving through a system. If it's a turbine, we certainly did one example with a turbine in 303, and you can define Bernoulli for that one-dimensional system in terms of this expression. We didn't use it we used it sparingly because we didn't do very much with thermal energy in the system, with enthalpy in the system. But you see that we have the velocity head term, the elevation term, and wrapped into the enthalpy, we have both internal energy per unit mass, which is this portion that is defined in terms of the change in the energy of the system, plus the pressure, instead of being with these terms, is just wrapped into the enthalpy. And so that's kind of the system that we'll deal with. We won't use it in this form. I think we'll just use it in the box form. This is a one-dimensional equation. You can write this in 3 dimensions if you use Reynolds transport theorem as well. We won't. And we'll tend to use it just in this form, where it's a 0-dimensional system instead of a 1-dimensional system. And yeah, I don't think we need. So that's just background information for that. So what we'll do is we'll kind of follow the text in Glassley's book. It's online if you want to grab it. I don't think you need to grab it. So see, these figures we'll use today and these notes are kind of derived from that. But we'll try and look at how we can evaluate the behavior of the system in terms of changes in pressure, temperature, and enthalpy in the system. And so we need to be able to define some things. We talked about many of these things last time in terms of the first law, defining enthalpy per unit mass as the sum of internal energy per unit mass and the pressure divided by density, the pressure of the fluid. This is the same equation that we just looked at, which is Bernoulli written in 1 dimension for flow in a stream tube, and written in terms of the energy that's in the system. And so with the first law taken care of, we can talk about the second law, that entropy always increases. We talked about efficiency last time. We'll define it again today. I guess just as recap, it's the amount of work that you get out of a system relative to the amount of heat energy you put into it. Can never be larger than 1 because you can't have a perpetual machine, and often is much less than 1, and it depends on the temperature the system works at. And of course the non-ideal gas law, where pressure, volume, gas constant, temperature, and coefficient Z factor for non-ideal gases defines the behavior of the system in terms of pressure and temperature. We talked about the Carnot cycle last time. I guess we talked about it in terms of temperature versus volume, and this is written in terms of pressure in terms of volume. Originally it was a box last time, you understand, in terms of square components in this, and now this takes just the contours of the changes. But this is exactly the same, and this is what we want to use. This is the thermal energy that's going into the system to the turbine. It's changing phase from a liquid to a gas at constant temperature. Temperature is not changing as you go from one to the other. And so this thermal energy in is driving an ability to now pull work out of the system, because now the volume has changed. You've gone from a relatively small volume to a relatively large volume because you're allowing it to expand as it vaporizes. That expansion is able to drive a turbine, and that turbine is allowed to take work out of it. I just changed this morning. If you got your notes before, it was work in. It's not, it's obviously work out. Once you're here, you try and remove heat from the system. You condense it. So you run it in cooler air. So maybe you start off taking it out of the reservoir at 200 C. You'd like to be able to cool it down to be able to get to, say, 20 degrees centigrade, ambient air temperature. Probably you can't get there, and that affects your efficiency. And so you condense it to get to here, get it to be a liquid, compress it again fully to being a liquid, and then the cycle keeps on going. So I'm sure you've seen the Carnot cycle in your other materials. And so out of that, for instance, if we take this expression we had before for enthalpy being defined as internal energy, so this would be internal energy per unit mass multiplied by density, I think, right? We defined it slightly differently. This expression here, right, doesn't want to get bigger unless I do this. So this term here is just our definition of enthalpy. If we multiply both sides by density, because it's unit mass, no, sorry, don't want to do that. If we multiply both sides by mass, and mass is kilograms. This is kilograms per meter cubed, so this is pressure. These two terms here go to being volume. And so pressure volume times internal energy per unit mass times mass, and enthalpy per unit mass times mass. So it's just enthalpy. So this expression that we end up with here is merely a manifestation of doing that. Same expression, nothing different. It's just that we've multiplied by, I guess we've multiplied by mass. So that's not that, is it? It's by mass. And so if you do that, you get this expression here. And so as a consequence of that, at constant pressure or at constant volume, both of these terms here, we end up being able to be able to relate the enthalpy to a change in heat content in the system, because there's no other components that contribute to enthalpy in our system, not pressure and not volume, because we're holding both of them constant. And in that case, we can define the specific heat capacity as a change in heat energy relative to the change in temperature that occurs. So you apply an amount of heat and you get a change in temperature, and the ratio of those is by definition the coefficient that is the specific heat capacity that defines the behavior of the system. So in each of those cases, we can define the change in enthalpy, which we've done already, right, for our reservoir between 2 kilometers and 10 kilometers, just as the product per unit volume of the reservoir as the specific heat capacity multiplied by the temperature it goes through. If we want to get the amount for the whole system, we just need to multiply the enthalpy by the mass and the volume, which gives us the total mass in the system, and that gives us the total amount of thermal energy that's available in that system. So we've done that already, so we won't go back to that. We can also define entropy as the change in heat within the system divided by the temperature change. Entropy always increases, disorder always increases. We can write the behavior of the system for a Carnot cycle in terms of temperature and entropy instead of temperature and enthalpy as we've done. And it looks pretty much the same as you just go around the system. It's just another coefficient that we can use to describe behavior. And so the first and second law are that. The third thing that we should talk a little bit about is Gibbs free energy. And Gibbs energy, we won't use it so much here, but we'll use it when we talk about changes in chemistry in systems. So when you change the temperature of a system, a fluid comes out, its solubility in water will change and its reactivity with other components will change. And that behavior is driven by the magnitude of changes in Gibbs energy. Not absolute magnitudes, but the directions in which Gibbs energy changes. And we can define that as the energy available in the system at a reference state, and therefore the ability of that system to do work relative to another system which is a different energy state. And so we can use, again, our definition of enthalpy, which is the internal energy multiplied by pressure and volume with the system. And we can define change in Gibbs energy as being a product of both the entropy of the system at some pressure and some temperature, and the entropy of the system, change in entropy of the system, at some given temperature of our system that we find ourselves. In addition to that, we can also look at changes in the system as you change temperature through the specific heat constant at constant pressure in each case. The units of these are the same as each other, and also the change in volume and pressure. So these systems are accounting for these individual components in this. Typically, we can take this to be 0, in which case we can define the change in Gibbs energy as just the sum of the change in entropy and the change in enthalpy and entropy of the system at some constant temperature. And I guess the only relevant thing to come out of this, or one relevant thing to come out of this, is that if we look at those first two terms that contribute to Gibbs free energy, ignoring the others, we can define them in terms of a change of state, right? So you start off with energy at some standard temperature and pressure, which you choose, and you change the pressure and temperature to some different magnitude. And then the differences in enthalpy and entropy that occur are just the constant temperature of the system multiplied by the entropy of the system change. This is just delta, right? This is just delta H. And this is just delta S. So it's just writing it out as actual finite derivatives. And so what you can do is you can define the energy of a system in terms of, has to be in units of enthalpy, right? Which are joules per kilogram in this particular, or kilojoules per kilogram, kilomole. I guess it's on a molar basis, usually per kilogram. Kilograms and moles are related for any particular substance. And if you look at how it changes for either a liquid, in this case, which is this curve here, which bifurcates into two here, one for 1 MPa on the top, and one for 0.1 MPa on the bottom. This is atmospheric, right? This is 1 bar, and this is 10 times atmospheric. So for a liquid, as you change temperature, the Gibbs energy, the change in enthalpy of the system, if you like, you think of it as change in enthalpy of the system, doesn't change very much. It doesn't matter much what the pressure change is, because the fluid as a liquid is pretty much incompressible. If you increase the temperature 10 times, you don't change the mass of the fluid very substantially because it won't compress. It takes up the same volume. Conversely, if you look at a vapor and you change the temperature, then the Gibbs energy in the system, in this particular case, you see it's increasing as it increasingly negative as you increase temperature. It's not decreasing, it's becoming just the scalar of the system is negative. And so depending on vapor at only 1 atmosphere or at 10 atmospheres, this is wrong in the book, then there's a big differential between them in the first place, and the gradient of this compared to the gradient of this changes much more. So in other words, due to the compressibility of the system, as you change temperature, you change the volume by thermal expansion, and as a result of that, the mass within the system changes as well. So one is much more sensitive to changes in enthalpy. So we won't use that much more today, but we will come back to that when we talk about chemistry of these systems, when we talk about it in week 5, I think, right? After next week. We talked about a closed system yesterday, Tuesday rather, not yesterday. We made the point that for our closed system and the first law, that changes in internal energy resulted from heat rate in and work rate out. If there is no net accumulation of energy in the system, then they have to be equivalent to each other. But it's not a perfect conversion because it's not 100%. So the efficiency of the system is really defined as the rate of how much energy you put in and how much work you get out of the system. It's never 100%, and so you can define it in terms of these relative quantities here. Or usually you define it in the way we defined it on Tuesday as a change in temperature. And I guess we wrote it as 1 minus T2 over Ti. And so this, if you can get down to the background of the system to be T2 to being absolute 0, then this term by definition will be 0 and the maximum efficiency of 1. Can never actually do that. And so you're left with being hindered, I guess, by the magnitude of the rejected heat temperature, which if you're in Nevada and you're putting it through a turbine and then you're wanting to recondense the fluid, it may be that you can't get your temperature of your fluid down below 50 degrees centigrade because the ambient air temperature outside might be 30 or 40. But if you're in Iceland, then you might be able to get it down to 20 because your ambient air temperature is 0 centigrade. And so if you use this in terms of degrees Kelvin, you can look at the thermodynamic efficiency of any system, but inclusive of geothermal systems, where the temperature that you discard heat to has an impact on the efficiency. And all this is this law plotted up as a function of the initial temperature versus the rejected temperature, and the rejected temperatures are these, and these are the initial temperatures on the bottom. And so if you work out that equation, 1 minus T over Ti, then in terms of efficiency, if you have a particular reservoir temperature, say 250 degrees centigrade, then not surprisingly, your efficiency is higher as you can reject to a lower temperature than if you can only reject to 65 degrees centigrade. And it makes a difference between about 10%, right? 10% change in efficiency. And so that's actually reasonably more than I'd have thought, actually, since these temperatures that you use have to be used in terms of degrees Kelvin. And so you have to use degrees Kelvin to do that. And so efficiency matters to us. And so for us, the temperature at which we're able to reject fluid to by ambient air temperature is controlling how much you can get out of a reservoir that comes to you at any given temperature. If your reservoir is at the critical point of water, which is 3 something, right? Is it 3 of the order of 350? Then your efficiencies go up slightly. So if you reject at 20 degrees centigrade versus this, then that's also a change in about 10%. So you get 10% gain in efficiency if you go up from a relatively hot reservoir to one that's at supercritical. And of course, the extra energy you get from the system is provided by the fact that the entropy is not just due to the temperature of this, but it's due to the internal energy that you have in the system at that particular temperature. So we can calculate what the thermodynamic efficiencies would be. So if you look at water, and we're typically interested in water because that's almost always our heat carrier fluid. We mentioned last time that it could be something like CO2. People have talked about circulating CO2 in reservoirs. Then we can look at, for typical geothermal fluids, what their behavior might look like and what the range of subsurface conditions would be. So this is also out of Glassey's book. It relies on the fact that we can take our profile with depth, and for instance we could calculate pressure versus depth. You know exactly how to do this. You know that pressure is, or stress is going to be equal to the unit weight of whatever multiplied by its depth. For water, we know that the unit weight is something like, well, not something like, it's 10 kilonewtons per meter cubed. For rock, we said it's about 3 times that. So it's about, let's say, 30 kilonewtons per meter cubed. And so you know that by the time you've gone down 1,000 meters, say, a kilometer, then you know that for water, well, let's do it for rock. For rock, you would be at 1,000 times 30 kilonewtons, so that'd be 30 meganewtons. And so perhaps it's easier to do it for water. So this would be, at 1 kilometer, it would be 10 MPa. So this would be a 1 kilometer, 10 MPa for water. This is MPa on here. So for water, 10 MPa, 10 to the 0 would be 1. This would be water, which would be 10 MPa. And so because the unit weight of rock is 3 times that, the same stress at the depth in the crust would be equivalent to a third of the height of water, right? So if the density of water is 1,000 kilograms a cubic meter, density of rock is 3,000 kilograms per cubic meter, you only have to go a third of the depth down. And so if this is 1,000 meters for water, then for rock, it's only something like 300 meters. And so in the same way we could do this, we could also replace this, I suppose, with temperature. And we know that temperature is given by something like temperature is equal to depth times dTdz. We talked about dTdz being what? It was something like 25 to 50 degrees centigrade per kilometer. And so you can do the same thing. So that by the time you get down to this, typically this would be not 0 degrees centigrade at the top, but say 10 centigrade would be a normal one, but let's ignore that. Let's assume that this is 0 at the surface. Then by the time you go down to 1,000 meters, 1 kilometer, you're either at 25 degrees centigrade or 50 degrees centigrade. So each kilometer down, you'd be something like this. So if you're scaling rock, all you're doing is, this is a graph of pressure increasing in this direction relative to temperature. And of course, we can plot these components on here by a depth of 1 kilometer should be 1 MPa in terms of water. A depth of the stress equivalent to that depth of 1 kilometer of water would only be 300 meters of the lithostat. And the lithostat is important because it's the maximum pressure that you can reach before you hydraulically fracture it and all your fluid escapes. So if your fluid pressure is greater than the weight of the rock on top of it, it will lift the rock. It'll make a fracture in it and all the fluid will escape. So a practical limit to the pressure that you can get at any depth is going to be the so-called lithostat. and that's what this is marked up against this. So lithostat is just this curve here when the unit weight is unit weight of rock. And so it would be this death trajectory. And so I suppose we can look on this at what the appropriate properties are. So 10 to the 0 bar is atmospheric. And so if we are at 100 degrees centigrade, 100 degrees centigrade would be 370 Kelvin. 73, right? At 1 bar, then 0 degrees centigrade would be 273 Kelvin. So these are the behaviors of water at 0 centigrade, 100 centigrade, and at 1 atmosphere. And this would be vapor, everything that's on the right side of this. This would be liquid, everything on the left side of this. And I guess this would be solid on this as ice, which would not be the case. And we can also plot within our system the correspondence between what might happen in this. So at 3,000 meters of rock, then I suppose what would be our temperature? At 25 degrees centigrade, 3 kilometers, it would either be 75 degrees centigrade or 150. So looks like this graph is a little off. 75 degrees centigrade is somewhere here. So, and 150 degrees centigrade is somewhere here. So it seems to me it's a little off, but these are the temperatures that are being talked about, different thermal gradients. But this swoop up here is just where the in-situ stresses, which are controlled merely by the weight of material above you, and the temperatures, which are just controlled by the geothermal gradient, are calculated incrementally for the same depths, moving up through the system, and plotted together. And so it defines a trajectory which is, I suppose, a lower bound for the temperatures on this side, and an upper bound for the temperatures at any particular depth. So if you're at 3,000 meters, you can calculate what that upper bound and lower bound temperatures are. And also plotted onto the top of that are the kind of ranges in which different geothermal systems work. So if you go to Nevada and look at the geysers and look at these native geothermal systems on plate boundaries, that's interesting. You're talking something in this box here, which intersects at obviously very high temperatures and very high pressures as well. So they're highly energetic. It doesn't show you what the enthalpy is of these systems here. If you're talking about direct use of geothermal systems, then those would be systems where you're not even at boiling point. It's not very useful to you as to generate electricity because you're less than the boiling point of water or thereabouts, and you're in this range. And then if you're in ground-sourced heat pumps, you're at even lower temperature. It seems to me that actually some of these temperatures here are pretty optimistic. So being at, I don't know what that is, being at 50 or 60 degrees centigrade would be an unusually high temperature in the subsurface. And actually being at 300 meters below ground would also be unusually deep. So ground-sourced heat pumps would probably be more like to being in this region here, which I'm not drawing very well. Down here. I think it's much too optimistic to being such high temperature and such high pressure. And so those are the ranges by which these systems work. We know what heat capacities are from those systems. So if we know what the system is, we can calculate exactly how much energy is in those systems from the temperature alone, if we know what the geothermal gradients are. We've done the calculation already, so I won't go through it again. If you use the specific heat capacity of water or the specific heat capacity of the rock, depending on where you're taking your heat from. We use this heat capacity of the rock because between 4 and 10 kilometers, or 6 and 10 kilometers, then maybe the porosity of these rocks is something like a few percent, which means that 97% of the material is rock and only 3% is water. So the heat that's stored in it is primarily rock. And we did the calculation with that just by using this expression: volume, density, specific heat capacity of the material you want, the change in temperature you expect to get. Then in rock, you would use the specific heat capacity of the rock. If you wanted to know what the energy you could get from the heat transfer fluid, so if it's water that you're bringing up to the surface to transfer the energy in, then the maximum amount of energy you can get is going to be actually higher than the rock, because it's going to be carrying it at the specific heat capacity of the rock. So 1 kilogram of water dropping through 1 K is going to give you 4180 joules, 4.1 kilojoules. And so that gives us the magnitude of heat you get by dropping it 1 degree centigrade. Enthalpy, if you calculated the enthalpy change between bringing it up at 100 degrees centigrade and dropping it to 99 degrees centigrade, from going through 1 degree, you get exactly the same magnitude for this. But the total enthalpy that exists in that system is going to be equal to the mass of the fluid, the specific heat capacity of the fluid, and the change in temperature, not just delta T due to this 1 degree centigrade change, but the total enthalpy is going to be the temperature in Kelvin. So it's at 25 degrees centigrade, it's going to be 273 by 25, which is this. And if you work it out, because this temperature change is something like 300 times the 1 degree Kelvin, the amount of heat energy between 25 degrees centigrade and absolute zero is 300 times that. So total enthalpy is always defined in terms of absolute temperatures. But we're typically interested in changes in enthalpies in our system to be able to understand what's going on. So another way to think about this in these systems, so this only gives us the range of pressures and temperatures that we might expect. Pressures are defined by the height of rock above them, which is the maximum cap on the pressure cooker that can hold in the maximum pressure due to the overburden weight. And so the maximum pressure that can be present due to the heating of the water can be the lithostat, which is given here. And the temperature that the fluid finds itself at and the reservoir defines together the amount of enthalpy. So if we plot those zones that were present in here between high temperature reservoirs, direct heat use, and geothermal heat pumps on a slightly different format, if we do it in terms of enthalpy, versus pressure. So this would be at atmospheric pressure, this would be going down progressively further in the crust. And so I'm not sure what 10,000 bars was in terms of depth. We can pull it off here. 10,000 would be 30,000 meters, so 30 kilometers. So this would be 30 kilometers. So this would be 3 kilometers. So the zone at which we're probably working, right, in 4 to 6 kilometers, if we can certainly drill 4 kilometers, 5 kilometers. You can't access it much deeper than this with current technology. Then the system that we're looking at is in terms of these zones just drawn in a different way. So these represent contours of constant temperature, as you have here. And it's useful to be able to realize that these kinks that you see here, so I didn't draw these very well, so maybe I'll remove them and try drawing them back. If you physically join up, can't do it here, if you join up these individual kinks, these represent the transitions in phase. So I don't know where this would go, say there. And if you do it for this. I guess I did it before. And you do this. Don't know where this one goes, but they join up. Then it looks a bit like this capped diagram here. So this is enthalpy on the bottom, pressure vertically. This is pressure horizontally, enthalpy in the vertical direction. And so you know this is the steam diagram that we looked at before. So all this region here is liquid water. All this region is 100% vapor. And the transition region, as you go across at constant pressure and temperature, is the transition from 100% water to 100% steam. And so if we look at the behaviors of water in the regimes that we're talking about in terms of temperatures and pressures, which were on the previous diagram, but it's just plotted in a different way as a function of enthalpy, then this represents the transit across at well, maybe slightly different from this, I guess. Yeah, the transit at constant temperature, right? This is transiting from constant temperature. So clearly at any given temperature, constant temperature and pressure, this is the component which is on the left-hand limb. So this is liquid, I guess, below it, right? Is that right? Below this blue line. This is vapor above here. And this is the transition. This would be 100% water. Or 100%, I guess it's water all the way, right? 100% liquid. And this would be 100% steam. And so this just allows us to be able to define the response of the system at those behaviors. So it defines our high-grade system, high temperatures and high pressures, our lower-grade system, which is this one here, and our very low-grade system, which has our ground-sourced heat pumps, which are, well, it's never going to be at 0.3 kilometers, 300 meters deep. Typically, they're 10 meters deep or less. And so it's much closer to this range. And the temperatures, well, 50 degrees centigrade would be optimistic as well. So really the zone for ground-sourced heat pumps would probably be in here, off the side. And so if we transfer this figure onto our steam chart, our phase diagram, then this would be ground-sourced heat pumps on this side progressively. So very low pressure, very low temperature, not 0 degrees centigrade. This is increasing. These are contours of temperatures as you go across here. So 350, this is 250, so 200, 150, 150, 0 in this. So I guess it is in this region here, and it's at relatively low enthalpies. So all this allows you to do is to be able to do exactly what we did last time. We'll do a little example that imagines that you're coming into a system at 40 bars. So if we go down here, so how much, I guess you could ask yourself, if you're recovering water from a system and you start with your system at 250 centigrade and 40 bars, we said that 40 bars is 4 MPa. 4 MPa would be 4 kilometers of water, or a third of that of rock. So a third of 4 kilometers is something of the order of 1,500 meters. So it's equivalent of 1,500 meters below surface, capping it off. So 40 bars and 250 centigrade. If you look at this diagram here, I'm going to remove these other parts because it just complicates it. Means that as you come down at 40 bars, so 10, 20, 30, 40, then you're right on this boundary. So at 40 bars and 250 centigrade, this is a 250 centigrade component, then if you bring the water up to the surface, then the pressure goes from being 40 bars to being 1 bar. And so the trajectory you go on is either down here or across here and then down here. So it depends on whether you will be at 100% water or 100% steam as to which one of these paths you take. So the easiest way to do that calculation is ensure that both the change in mass, so in other words, there's no volume change as you come up. So you're bringing yourself up so quickly that there's no change in mass, but you also bring yourself up so quickly, the fluid up so quickly, that there's no change in enthalpy. So this packet of fluid that comes up has no time to be able to adjust. So if it does that, then by definition, if it keeps the same enthalpy, then on this curve, clearly it has to go on this trajectory. So we know that when it's in the ground, it's at something like 1,000 plus kilojoules per kilogram at this particular point. As we bring it into the system, we're going to end up at this point, because by definition, if it's initially at this state and we don't allow it to change its enthalpy, it has to come out and have this amount of energy associated with it. And I guess what we don't know is what it would look like. Is it going to be water, or is it going to be steam? And we know exactly what it is. You can pull it off this diagram, or we can figure out independently exactly what that is. It's going to be something like, this is about 30%. This is 100% water, 80% water, liquid, 70%. So it has to be something like 70% liquid plus 30% steam. And we can get that from what we talked about last time. We talked about these proportions, the linear proportions. So as it goes, if it scoots across this at 1 bar, then it's isothermal. It has no chance to change temperature. But what it's doing is it's changing its enthalpy because it's changing state. It's going from a liquid to a gas. It's expanding by definition, but it's not changing temperature because there's no heat supply to the system. It's just changing its internal energy. And so we could calculate exactly what this proportion of steam to liquid would be merely by taking the magnitudes of the enthalpies at these two locations. The enthalpies at 100% steam and 100% liquid, or this enthalpy here. So if we take those magnitudes here, so this is what we know the enthalpy is going to be. So we could use our relationship, and I realized today that it's slightly different from our relationship from last time. Remember last time we said that if we know what the entropy or the enthalpy or the mass is at one temperature, we can link it by x times enthalpy plus 1 minus x times the enthalpy equals our true enthalpy. So this is the enthalpy we start at. So this has to equal, I think it's 1085 kilojoules per kilogram. So that's just this term here. So this is the magnitude it starts at, which is 1,000 and change enthalpy in terms of kilojoules per kilogram. This is what we know it has to be wherever it is at this point. If we don't have this diagram, we don't know what this point is in terms of its percentages. But if we know what the enthalpy is of liquid, and we know what the enthalpy of steam is, and so the enthalpy of liquid is going to be what? Something like 400 kilojoules per kilogram. And the enthalpy of pure steam is going to be something like, I don't know, 2,600 kilojoules per kilogram. So these are the two numbers that we use. So this is at 100% water, and this is at 100% steam. And so we could merely write this equation that we have here in terms of that. So this term would be this. This would be liquid versus vapor. So liquid was something like 4. It's written down here. So this is 400 kilojoules. This is kilojoules. This isn't. It's 400, and this 2,000. So it would be X times the liquid, which is 419 kilojoules per kilogram, plus 1 minus X times 2676 kilojoules per kilogram. So this is the enthalpy we come into the system with at depth, right? This is the properties for water at this particular pressure and temperature. This is the property for water at this of steam at this particular pressure and temperature. And if we know those two n values, we can calculate what this percentage is. And if you do the math, it comes out as something like 70%. I did it for. Well, it's easy, right? It's something like 1.1, if you take this away, is equal to 0.3 times 0.419. I'm just rewriting this, not in thousands, but in units. And this is 1 minus 0.3, which is 0.7, multiplied by 2.676, just to make it easy by taking the thousands out of this. And if you do that calculation, you'll find out that, because this magnitude is x, right? This magnitude is x, and x is the proportion of water, and 1 minus x is a proportion of steam. And so you can do that calculation, and you'll find out that it turns out to be something like 30%. I think this is written the wrong way around. X is the liquid fraction, definitely. So X is this is 30%. We defined X the other time. Someone's calling me. My daughter's calling me. I guess I won't accept that. I wonder why discipline is. My phone's going off in my pocket. So that's good. I think in this class we've had a text from my son, which was telling me to watch Tiny. What's it? You must have watched it. What is it? Tiny Desk Music? Tiny Desk? Yeah, whatever. It was some band, which is, that came in here to this class as well, I think, the other week. Tiny Desk concert, yeah. He was recommending something to me, which I thought was quite interesting. And so, yeah, hopefully it's not an emergency. Yeah, well, that's it, yeah. So last time when we did it, we talked about defining this equation here. We defined X before was equal to the mass of gas, in this term, mass of vapor divided by the total mass. In this one, we've defined, out of Glassey's book, it's defined in terms of the mass of liquid divided by the total mass. That's the difference. But that's all it is. So the manifestation of this this figure, this table, with these contours, is only just using that equation. So if you don't have, obviously in this case we can just pick it off because we can see that 70% liquid. These are gas fractions, 100% gas, 80%, 60%, 40%, 70% gas. Sorry, doing noise. 80, 60, 40, 30% liquid, which has to be 7% gas, right? This is the 70% goes here. And this is the 30 that goes here. So that's it. So I think that's it. I mean, it's nothing more than that. I mean, we're not going to use Bernoulli's equation beyond this, but merely make the case that what we've done in fluid mechanics really was kind of first law stuff. Our extension in fluid mechanics was to have a one-dimensional system, which is a stream tube that has a mass flow rate in it, had an influent enthalpy, had a velocity of the fluid, and had some elevation changes in it maybe, and was merely balancing the thermal energy in and the work energy out. And so I suppose you could think of it in terms of Bernoulli, in that when we usually, I'm getting a bit, I see we have a bit of time, so I'm going to use it. You can think of it in these terms, and I think it's useful to think, is if you have your Bernoulli system written like this, and we've often kind of drawn them in terms of a vertical component. I suppose you could have a datum which is z equals 0, in which case this would be z1 and z2. It would have a velocity coming out of here, v out or v2. We can draw the grade lines for this between these, where this grade line would be p over gamma, a grade line for velocity between upstream and downstream. This would be velocity squared over 2g. And so in this pipe, we could have, this is our energy grade line, what we call EGL. And if there's no frictional losses in the system, it can be has to be horizontal. This is Bernoulli's equation. If there are losses in the system, then what we can do is we can provide a pump head to this. And physically what that does is it takes this value upstream and it adds a pump head. Goes across here. And then this, to get it down here, has to be a head loss, right? And the head loss is due to friction factor. So putting it in context, what head loss is equal to friction factor, length over diameter of the pipe, v squared over 2g, right? So we can define this. But the point is, I suppose, in looking at it in this term, this is some work we're putting into the system. So this net shaft work in is kind of this pump head, which is being put into the system. And of course, to get that pump head, it runs on electricity. And to get electricity, we need to typically put heat into a boiler, run it through a turbine, get work out of it. That work is electricity, put it into a pump, and it runs your system. And so it just, maybe it's useful to put it into context, is that this is really all we're doing. Except we're not worrying at all about any velocities in our system. We're not worried about any changes in our system. We're just looking at the second law, the first law, written in terms of these components for the Carnot cycle. And the only points we worried about are the magnitudes of the enthalpy per unit mass, which is equal to internal energy per unit mass plus pressure over density. And so this is the term that says something about pressure, and the temperature is thrown into this part here. That's it. And we're dealing it not with a one-dimensional system or a two-dimensional system or a three-dimensional system. It's merely a zero-dimensional system, a box, a bucket if you like, that where you're accounting for the mass that goes in and you're accounting for the work that goes out, not the mass that goes in, the thermal energy that goes in, the work that goes out, and any difference in internal energy is defined by here. And this internal energy can be defined most conveniently to include the influence of pressure, because a reservoir at depth not only has temperature associated with it, but it also has a certain amount of energy in compressed strain energy, which it can also deliver when you reduce the pressure from 40 bars at depth to 1 bar at the surface, because it'll expand in addition to the phase change effect by the temperature. So these are combined behaviors. Perfect. Half an hour before gives me time to get to my next class. So that's it. So that's all we'll talk about thermodynamics. And so an important term for us, really, the only important term for us in this is understanding enthalpy changes. We need to know how fluid works as a heat carrier. It carries enthalpy with it. And we need to know how we convert that enthalpy into energy, and that's usually during phase change. Sometimes it's phase change of the geothermal fluid itself in most deep hot reservoirs. You'll flash it to steam, and then maybe some of that will off gas, and then you'll collect some of it by condensing and pump it underground. But both in geothermal heat pump systems and also in binary systems, if you flash to steam and you bring your temperature of your water back to 100 degrees centigrade, you can still get electrical energy out of the difference in temperature between 100 centigrade and 40 centigrade if you have a flash fluid that will change from liquid to steam, to vapor, I guess, not steam, at 40 degrees centigrade. So you take the 100 degrees, you transfer it to this heat transfer fluid that vaporizes at 40. It generates electricity, is condensed back to below 40, and then used in a system. And of course, that's the essence of a heat pump, is that it brings water in to your house. It brings it in at the temperature of the subsurface soil, which is about 10 degrees centigrade only. And of course, from what we talked about before, if you look at the difference in temperature as you go down within the surface, the maximum temperature in the summer is 30 degrees centigrade maybe. The minimum today, it was -4 Fahrenheit for me, so that's -36 Fahrenheit, so that's about -15 centigrade. And so somewhere the midline between that is roughly 10 degrees centigrade, not exactly. But the summertime temperature takes the ground profile up to this. The wintertime temperature takes the ground profile up to this, curved. And at some depth below the surface, maybe 10 meters, the effects of the the seasonal variations get damped out, and it's the average of these two. And so the water that comes into your house year-round will come in at about 50 Fahrenheit, 10 degrees centigrade. And so in the wintertime, you use some of that relatively warm water to scavenge the heat energy out of it to bring the temperature of your house up above the outside temperature. And in the, did I say summertime? In the wintertime. And in the summertime, you use the relatively cool water to bring the heat of your house down from the outside temperature by using the cooling influence of that. And it's not by using it directly, it's by using this fluid with a heat change fluid, in an air conditioner basically, with a phase change, to be able to very efficiently recover, scavenge the heat from this, the water that's coming into your house, and put it into the heat pump, and therefore put air out that is at some other temperature. So we're interested either in the geothermal fluids themselves, or using those geothermal fluids to influence phase changes in other fluids. A binary plant system for a big geothermal project, or a ground-sourced heat pump, they work on exactly the same principle, except a ground source heat pump, I guess, doesn't generate electricity. It uses the phase change to suck heat out of the water that comes in at only 10 degrees centigrade. That's it.